Hello and welcome to Cashmatics. In this lesson we'll be looking at radians. I'm going to be telling you what a radian is, how to convert between degrees and radians, why we need to learn about them, and why you can only do some maths with radians alone. So grab yourself some paper and a pen and let's get started. There's many different units we can use to measure different things. So for example, a length you can measure using yards or meters. Temperature you can measure using degrees Fahrenheit or degrees centigrade. And the same goes for angles. Now up till now you've probably been able to measure angles using degrees, but there is actually another unit we can use, and that is radians. So the first thing we need to do is define how big a radian is. So take a look at this picture. I've got a sector of a circle, and you can see there's an angle theta in that sector. Now the definition of 1 radian is the angle through which you'd have to turn so that the length of the arc is equivalent to the radius. So this length here is going to be equivalent to the radius. So if you were to turn through 1 radian, that length would be the same as the radius. And although this isn't drawn to scale, it's not that bad. And there'd be 6 of these, approximately 6 of these in a circle. Okay, the exact number of radians in a circle is 2 pi radians in a circle. Okay, that's the exact number, which is roughly about 6.28, but we tend to write everything in terms of pi. One of the first things we need to be able to do is convert between degrees and radians. So I've already told you there's 360 degrees in a full turn. Well, I didn't need to tell you that, you should already know that. And that's equivalent to 2 pi radians. Okay, and I want to convert 360 degrees into 2 pi. So let's just focus on the numbers and see what happens with the numbers. Now over here I've only got a number, here I've got a number with pi, which means I need to introduce a pi. But if I did that, I'd get 360 pi, but I only want 2 pi. So I need to divide by 180. If I was going back the other way, I've got 2 pi, so I need to multiply by 180 to get the 360, but I also need to get rid of the pi by dividing through by pi. So please remember how I've done this. This isn't going to be given to you in any formula book. Now with enough time and practice, you'll hopefully remember this, but just in case you forget, try and remember what I've done here, and hopefully you'll be able to work out the rule for yourselves. One other thing, sometimes when it comes to radians, you might see this symbol, so you might get 2 pi with a little c. So some people use a little c for radians rather than the rad, but that doesn't happen that often, but just make sure you're aware of it just in case you do see it and get confused. So as you've probably guessed, you're probably going to need to be able to convert between degrees and radians. So I'll just do a couple of examples and then I'll give you some to do. So let's do one here. So we've got 300 degrees, so I need to multiply that. So 300 multiplied by pi divided by 180. So what I need to do is simplify this part of the fraction, so the 300 over 180, which gives me 5/3. So this becomes 5 pi upon 3 radians. If I was going the other way, I've got 5 pi upon 6 here, so I've got, say, 5 pi over 6 multiplied by 180 and divided by pi. So the pi's cancel each other out, and if I did 5 times 180 and then divide by 6, I would get 150 degrees. Now what I've got here is a lot of angles for you to convert. The table on the left shows you a lot of key angles which you could really do with committing to memory. So convert those into radians and try and memorize those if you can. But to be honest, you're going to use them so much that you should actually just remember those. The one on the right is just some random angles, some in degrees, some in radians. Just try to convert them. Pause the video, look back if you need to, okay, and I'll reveal the answers shortly. Alright, so I hope you've had enough time to do those questions. So I'm about to reveal the answers, and there you go. So just check through those, and if you've made loads and loads of errors, you probably need to go back and look at the example again. If you haven't, and you got most of them right, we can move on. And one last thing before I go, I'm going to show you 2 triangles. Now before you say, I know you can't see true triangles there, you've got a square there as well. I'm going to extract two triangles from there. So the first triangle is an equilateral triangle with side length 2, and the other one's a square with side length 1. And what I'm going to do is I'm going to split the triangle in half and extract half the triangle. I'm going to split the square in half as well and extract a triangle from it. So if I do that, this is what I get. And what I'm going to do is I'm going to put on some angles and some units on here. So that's 2 units. This is half of the original triangle, so that's 1 unit. And using Pythagoras, I can work out that's root 3. For this triangle over here, that'd still be 1 unit, and that'd be 1 unit. And using Pythagoras, that's 2 units. Now, in terms of the angles, this angle is still pi over 3. Remember, pi over 3 is 60 degrees, and 60 degrees is the angles in an equilateral triangle. This here would be 30 degrees, which is pi over 6. And this over here is 45 degrees, which is pi over 4. Now, why are these triangles so useful? They're useful because of the 3 key angles you've got here, pi over 3, pi over 6, and pi over 4. These turn up again and again and again. And I tell all of my students to try and remember to be able to sketch these triangles within a matter of seconds. And if I was to do them, I could have sketched these in 4 seconds on a piece of paper. Well, 4 seconds each. And actually, I'll have to challenge myself on that. But it won't be far off that. And the reason for that is because they turn up so much, you don't want to be fiddling about with the calculator checking things. And if you see certain ratios, you should just recognize them and understand we're talking about some key angles here. So, for example, if I wanted to work out the sine of pi over 3, okay, the sine of pi over 3, here's pi over 3. The sine of pi over 3 would be the opposite divided by the hypotenuse, so that would be root 3 over 2. If I wanted to work out the tan of pi over 6, so here's pi over 6, tan is opposite over adjacent, so 1 divided by root 3. And you can rationalize that if you want. Or you might want to work out the cosine of pi over 4. Okay, and the cosine of pi over 4 would be the adjacent divided by the hypotenuse, which would be 1 over root 2. So these triangles are actually invaluable, and those triangles together with the curves of the functions, so we've got the curves over here, you've got 0, you've got pi over 2, you've got pi, and you've got 3 pi over 2 and 2 pi. So this is the sine curve. You can easily see the sine of pi over 2 is 1, because remember this goes up and down between 1 and minus 1. The sine of pi is 0. The sine of 2 pi is also 0. So being able to sketch these curves quickly and being able to sketch these triangles quickly will save you a lot of time and a lot of bother. Right, so I hope that's helped you to understand radians. I'll do a separate video on how we can use those to work out the length of a sector, the length of an arc and the area of a sector. And in future videos, when we look at integration and differentiation, I will show you why radians are the only way to measure angles for those kind of functions, and it is the only true way of measuring angles. Anyway, I hope that's helped you to understand them, and I'll see you next time. Goodbye for now.